Hello everybody, this is Fahad Al-Harbi. Today I'm gonna present some examples in my field curriculum and teaching that I can use some non-parametric methods to find the result about for my data. So I will use two type of tests. The first test is cross-call Wallace to test between if there is any differences between groups, and also we might have type 1 error, and we need like adjustment to control that type 1 error. So I will talk about some adjustments, especially the Banforani. I will talk about with more details about Banforani and why we need to use the Banforani for adjustment and what's the theory behind that. And also I will give the summary about the other type of adjustment to control the type 1 error. Also, I brought an example and for the correlation tests to compare between to the independent and dependent group to find out if there is any relationship. So I will use the Pearson and Spearman test, and then we will make the conclusion which one is more appropriate for our data. So let's start. So for the course qual wallet test to compare between a group, I have this research. The research wants to examine 4 types of writing activities: summary, take notes, answer short questions, and writing response. Actually, the researcher want to find which activity is more effective to improve student reading comprehension score. So each group they will learn about that specific activity, and then they will be given a passage. So they read it and they will use that strategy, and then they will be given 20 multiple choice questions, so they can answer those questions based on the technique and the writing activity that they use. So here is our hypothesis. The research hypothesis is there are differences between the rank mean of the fourth group. So we can see we do not use the mean, we use the rank mean. So we used like the non-parametric technique. This is the cross-call Wallace test. So we will use the rank mean for the fourth groups. Okay, here is our data. So we have the summary. There was 6 subjects. For the take notes, 6 subjects, and for the answer short questions there is also 6 subjects, and also for the writing response there is also 6 subjects. So we will have 24 subjects for this data, and the scores it's from 1 till to 20. And here's the R code for those data for each group. So we will make like the permutation shuffling for more than for 2000 time, and then if we find significant result, then we will do the follow MPOS test to compare between A and B, A and C, or A and D, and all of them until we cover as possible as tests we have. So here is our histogram. So we can see it's not normally distribution, so we cannot trust the mean in this case because it's heavy tail. So this is why we need to use the rank mean instead of mean. So after conducting the course-qual Wallace test, here is our result. We find there is a significant among the rank mean of the 4 groups. So it's our significant, it's highly significant. So there is at least 1 differences among those groups, and we need to do follow up MPOS test and to provide more details about how those groups compare to each other. And here is the R code for those. So we will use like A and B, A and C, and A and D, and so on. So until we cover the 6 comparison group between group. So, and here is the result that we got from that comparison between the summary and take notes. Oh, there is a significant result. While there is no significant result between summary and answer questions, there is a significant result between summary and writing response, and there is also a significant result between take notes and answer short questions. And while there is no significant result between take notes and writing response, and eventually we have significant result between answer short questions and writing response. So we have four significant result. The question here, can we trust this result? Do we might have type 1 error because of doing all those multiple tests on the same data? So here what we did, we start with an ambiguous f-test to see whether something is going on, and then we follow up with contrast to test for interesting effect that might explain the significance between group variability. And then after a while, and we did all those tests, we might identify a number of superior findings. So we have four significant results among the six tests. So here is our concern. We might have type 1 error. There is at least one error that we made. So what what exactly happened? What is our problem when we say we might have type 1 error? What's happened? It's called family-wise type 1 error. As you increase the number of the tests, so that what does it mean? So our alpha level is equal to 0.05, which is point 1 minus 0.105. So this is our true negative rate. It's 0.95. So our negative. So here is the equation when we make like 1 minus 1.05. So here is our true negative rate. So what's happened if we have many significant tests on the same data? What happened to this equation? So if we added another independent significant test, then the probability of not making any type 1 error would be, so here our true negative. So let's say we have two tests, then multiply to each other, so it will be decrease from 95%, 0.95% to be 90%. So we will increase the type 1 error that we might have it among those two tests. So the family-wise one error that we have, the family-wise error, it's like probability of making at least one type error, as I said before. So here when we conduct more significant tests, the chance of making at least one type 1 error. So here we can see this is for the 0.05. As we increase our number of tests increases, so we can see how the magnitude of those, if we increasing the type 1 error, this is for type 105, and here is the number of tests that we might did it. So it's very clear right now. We can see that we might, as we increase the number of ambiguous tests, so our probability of increasing type 1 error also will be increased. So what to do? What do we need to do to control this type 1 error? So there is two things we need to do. One of them, the first thing is lower our alpha level, or increase the necessary critical value of rejection of our rejection hypothesis. So these are two sides of the same coin. The only risk we will run is that lowering alpha level also lower the power. So controlling type 1 error, there is a number of suggested procedures. The Bonferroni adjusted, which I will talk within details about it today, and Fisher and Tukey and Chevy procedures. And there is many others procedures, but only I will cover the Bonferroni mostly. And here just I want to mention some details when to use Fisher and when to use Tukey and when to use Shafi, what's the appropriate way to use it, and the good time to use those. So here we, as I said, we need to lower our type 1 error, but also lower the power. So here's about the Banforani adjustment. This is the most popular adjustment that use in the real world. People use in the real world because it's recommended to if we have like less than 10, equal or less than 10 tests to use the Banforani adjustment. The Banforani show that the increased type 1 error rate from multiple tests will always be less than multiplying our original alpha level by the number of the tests. Here is the picture of the Banforani inequality. So the increase of type 1 error rate from doing multiple tests will always be less than how many times we do so than the original alpha level. So the family wise, our family wise or our new alpha level, it's usually less than original alpha level, which is might be like 1.05 or 0.01. So if we divide both sides by the number of tests that we are doing, so our alpha level will not be greater than original level. So determining the Banforani, how to determine? Dividing the original, the 0.05 by how many tests we did it, like 6 times as we did in our example. We did 6 times, so we need to divide our original alpha level 0.05 by 6. Then we will get the new our new value. So family-wise time rate will never be greater than original value. This is very important about the Banforani tests adjustment. So the type 1 error, here is the equation for that. So you can see right now, here is the 0.05 without adjustment. Even though we will do 5 or 10 or 15 or 20, it will be the same. So this is why the rate of being in the type 1 error is very high. But under the Banforani adjustment, we can see as much as we tests, our b value will be decreased. So this is why we might get away from the type 1 error. So here's the Banforani pros and cons about this type of test. It's very conservative to protect us from making at least one type 1 error. So it's like great deal to deal with statistical power for each individual test, and also it's our protection that it will be our Banforani adjust b value, it will be less than 0.05. For this reason, Banforani adjustments are most common with relative a few tests, so it should be used for 10 or less than 10. So here is the summary and procedures about some the Banforani and comparing with the other type of procedures. So as I said, it can be used in any situation, typically done with 10 tests or less than that. And also here is the Tukey. It can be used with testing how many group you have, dividing by the pairwise comparison. And Shafi can be used in any situation, typically done when the test that you will do greater than original expected. And also here is the unadjusted. Usually we did like the Fisher, there is no adjusted, no any kind of adjustment. So we might have type 1 error if we're using Fisher, if we have more than 2 variables that we want to compare between them. So it can tell us how much power we need to choose to adjust and choose which adjustment that appropriate for our tests. So compare tests that LCD find significant that adjustment did not. Here is in our example. So here is our example. As I said, we have 4 significant results. But how about after we take the Banforani our new value. So we will choose the Banforani because our data, our test, they are less than 10. So we better choose the Banforani adjustment. Here is our new b value. It's 0.008, which is less than original value. So after comparing our new value to the result, we only find type 1 error that we might have done before. It is the comparing between the take notes group and answer short question group. So we do not. So after using the Banforani, the comparing between those groups, there are not significant differences. So Banforani protect us from doing this kind of mistakes or type 1 error that we might have done if we do not use the Banforani tests. Here, right now, we're gonna move to the correlation, and I will use an example that from my field. The researcher want to examine if there is any relationship between the student reading score and writing scores. So we have a data. We want to compare between those groups. So we have, this is the reading score and writing scores. It's starting from 0 till 100. Just want to compare between those groups. There are 20. I mean, we have 20 individual students. They got like reading and writing, the same individual. I just want to compare between them. Here is the R code for Pearson correlation. And here is the Spearman test, the code for that I used for this test. So here is my result. After running after running the permutation test for Pearson correlation, there is a strong positive relationship between reading and writing, and we can see it's at two tails. There is 0.98, which is very high, that we have high correlation between them. While after conducting Spearman test, we find a significant, strong positive correlation between reading and writing, but it's less than Pearson. So we can see it's 0.79, and there is like a little differences, but which one we could conclude and we could trust, the Pearson correlation or the Spearman correlation. Actually, because there is a difference, as I said, in degree of relationship, the question here should be asked is which measure association would be appropriate to find their association.